had the desire to go to space since I was as old as I can remember anything, basically. It was something that drew me. Just looking at the moon, was enough. There's a destination, that you can actually see. And for me, that was something that called out. So the same thing happened with my husband, and we co-founded this company, Interorbital Systems, in 1995. Really out of a desire to fly to space destinations ourselves. We knew that NASA wasn't going to swing by and pick us up, so we had to make the you have to make the boat yourself, basically, in order to go. So we started with absolutely no budget. We started in a borrowed garage, not even our own garage, and we began working through the world's oldest experimental rocket society, the Pacific Rocket Society, which was dedicated to making real rockets, real liquid propulsion engines. And we were mentored by some of the greats in the industry, people from the Apollo program, people who worked at the various aerospace companies in the Los Angeles area, like Marquardt, a North American, some of the ancient companies. But those fellows had really secret guild knowledge and the black arts that you need to do rocket science. And unfortunately, that knowledge will soon be lost if we don't try to capture it from those people who are quickly disappearing. When the space shuttle came in, the knowledge that was usually transferred through making the traditional types of rockets that took us to the moon and still launch our satellites today. A lot of that knowledge was lost and was not transferred. And it is very much an apprenticeship system. So we try to gather as much as we can so we don't have to reinvent the wheel. And it's actually paid off. We have 4 people from that era on our team currently, and we're thankful for them. I'd like to introduce you to the company. Our main goal is orbital, lunar, and interplanetary transport. And the types of rockets we're making are bipropellant liquid rockets. This is a photograph, a recent flight test of what we call the CPM. It's a Common Propulsion Module. It's common to every augmented type of rocket system that we make. If you look at the rendering to the right, that's a rendering of 5 of these CPMs joined together, giving us an orbital launch vehicle. So I'll go back to that original garage where there was no money. And we found that working with the PRS, or Pacific Rocket Society, we found that people there were building these bipropellant liquid rocket engines, things that would cost millions, say if Aerojet or Boeing or someone else made them, and they were doing them for like under $1,000 or $2,000. We're thinking, wow, like what's wrong with this picture? Why should it cost millions, for the same kind of development as, it's something we could do, on our own. And when we made our first engine, it was a liquid oxygen and methanol engine. It was 2,000 pounds of thrust, and it was firing that and feeling that power and seeing it work, and doing it for under $1,000 was a revelation. So we like to say that we were kissed by the flame that day, and we knew there'd be no going back. So from that day in 1994 through the present, we've been engaged in making this happen. And we work out of the Mojave Air and Spaceport. Down at the bottom there's an engine firing. That's a test for this flight vehicle's engine. It's a 24-foot long plane there, by the way, at the bottom. And that's nitric acid and turpentine. We're the only people in the U.S. today using that propellant combination. But because we use it, we don't have to have a giant cryogenic infrastructure to keep other types of propellants like liquid oxygen and other things cold. These propellants are storable at room temperature, and we can buy them in a standard industrial fashion. We founded the company, again, in Mojave. We needed a remote location. We had actually been in an even more remote location working with the PRS, but if you forget a screwdriver or a bolt, you know, it's like a 2 or 3 hour drive back to civilization to try to find it. So we decided Mojave was a little better, it's a little more civilized, and they had a hardware store. So that was a main deciding factor. Plus, it was open. The people there who had founded the airport district, it used to be called the East Current Airport District, and a visionary named Dan Savovich had set it up as really an experimental station for people developing novel types of aircraft. When we came in, you said, hey, we've got some weird requests. Do you think it'd be possible if we maybe did some rocket engine testing here? I said, oh yeah, there's actually one other person here already. So, and it was Gary Hudson who went on to found a rocket and a company called HMX. So the two companies were there in 1996. We established and built these test sites. So we have 2 of them. There's the one at the top has very large tankage, so we can run long engine burns like we would need for orbital operations. And the lower one is where we test our current engines. Those, and again, back to that garage, that's the no budget aspect of the program really drove us to do an engine that we could afford to build. Now, if you are in a standard aerospace program, generally there are millions and millions of dollars that go into gigantic million-pound direct engines. And who can afford that? If it blows up, you're out of business, right? You've saved up all your pennies. You get that big engine built and it doesn't work. You might as well quit at that point because you have to go back through raising money again. But if you build something that you actually can afford to build, that translates into lower costs all down the line. So we decided to build a small engine and then augment that thrust by grouping multiples. So we have a 7,500 pound thrust engine currently. That's the core engine for our entire program. When we want something that'll lift 24 small satellites to a 310 kilometer orbit, we use 5 modules. That's the minimum we can use to get an orbital vehicle. It'll actually take something to orbit and allow the satellites to stay in orbit to give us that velocity. If we want to do something like a moon launch, which is coming up in around 2016, 2017, we'll be using a 36 module, but still with that 7,500 pound thrust engine. Okay, so we could afford to build it. It makes it cheaper for you. Right? And so this is it's completely counterintuitive to the way the aerospace system or industry runs today. And you know, Steve Jobs always said, think different. Well, this is different. This rocket engine is different. This rocket is different. Everything about it is it. And also, I don't want to confuse you with that, but there are, in the 1970s, there was a company called Otrog that came out of Germany, founded by Lutz Kaiser, who worked on the Apollo program. He was the one who came up with the bundling module idea, and now he works with us, which is pretty lucky because Otrog had in its hierarchy of managers the Wernher von Braun, after Werner left NASA, and Kurt Debus, and all the luminaries from the Apollo program. So having Lutz working with us is a tie to that original time when people were inventing rockets. We do prototyping and testing currently. We're testing all systems that will be used in our orbital vehicles. In the meantime, we're selling satellite systems and satellite kits that will be the passengers on these launches. So we fund ourselves that way. We're largely self-funded, which is another difference. with our company. We had one NASA contract for the development of this vehicle, small contract, but everything else has been raised through our sales and other activities. But as you can see, there's some elaborate infrastructure there, and we built it all. It's what they call sweat equity, and believe me, Mojave does a lot of sweat. It was definitely an unusual climate. But we have a very small team. This again is sort of counterintuitive for the aerospace industry. Usually when somebody starts a company, they immediately build a building and hire 100 people. Okay, well, we don't work that way. We work like the old style rocket team, where 12 or so people do kind of they are cross-trained basically. They do all jobs. The same people who design the rocket also build the rocket, test the rocket, launch the rocket, and raise money to do more. So this is different. This is a different kind of, that cross-training is unusual, but we make it work. And if somebody comes in with maybe 3 of the required skills and they don't have the 4th, well, we teach them how to do it. Maybe they're great at orbital mechanics, but they can't do composites. Well, then we show them how to do composites. But we have a varied team from every ethnicity, every gender, and it just works that way. We have kind of a Socratic setup where people can give their own input if they have a different point of view on how something should be done. The main designer will listen to it, not just like, oh no, I'm a designer, I know that. People will interact. And we find that beneficial to have a diverse workforce, and that in our opinion, gives us a better product and a better outreach to our customer base. We have, in addition to our Mojave facilities, these rocket test areas. Behind that big flame at the top is actually an underground bunker, which we also built, but we're in there. Well, that's right. And the location at the bottom is a flight test area that was set up. 3 organizations use that now: Reaction Research Society, Pacific Rocket Society, and the Friends of Amateur Rocket. It's one of the few places in the world where you can actually fly the rockets you build. And we can get waivers from the FAA up to 100,000 feet, which is pretty significant. And again, very pretty much American, I think. I tell people from France and England and Australia, they have some activity in Australia, but nothing like this. Nothing where you can go out this weekend and do your rocket work and have the freedom to engage in things like this, which would be illegal in most parts of the world. So that's one benefit. I'll talk a little bit about the way the system works. Again, this Common Propulsion Module, or CPM, is it's the most Spartan rocket in the world. It's the most radically streamlined vehicle that ever was. And we've taken out the failure-prone and expensive systems like turbo pumps. We don't need those. We use what's called blow-down pressurization to force the propellants through the engine. We use standard building and manufacturing processes that you might find in, say, the shipbuilding industry or other types of manufacturing. Excuse me. The engines are again manageably sized, made for mass production, as is this entire unit. This is the essential core of everything we do. So even down to the propellant, so we don't need an ignition system. We have what's called hypergolic ignition. The chemicals ignite on contact. So that's an assured spark. You don't want to be sitting on the moon, getting ready to go back, and then there's no spark, right? In our system, you just open the valves and you have fire. And we have our system set up so that in case there's a problem with, say, the system that would normally open those valves, you can go in and manually open them and get back to our. So that is a different approach as well. This particular rocket, because it is a standalone rocket, can serve as what's called a sounding rocket or a research rocket. It's launched from this mobile launcher. And we can, with this rocket, with a full performance version of it, we can take 145 kilos to a 310 kilometer altitude, which is pretty extraordinary for a small rocket. This one will fit inside a cargo container that was built with transportation on regular highways in mind. So, and also ship transport if we need it. So it's called the SR-145 when it goes off on its own because it can lift that capacity. Now we have the main engines, and then we need to steer the rocket. So we have what are called Vernier rocket engines. They're tiny thrusters that give us pitch, roll, and yaw, and allow us to steer the vehicle if it's going off course. And it's basically a giant robot. Okay, and these are the corrective mechanisms that if the robot senses it's not going in the right direction, these will take into action and apply thrust where needed and keep the vehicle on course. And it's in this test, this is also at the Mojave Air and Spaceport. we were able to prove the viability of this type of engine, and in the process of creating this propellant combination, we actually created a substitute or an alternative for the really dangerous hypertonic propellants like hydrazine or UDMH, nitrogen tetroxide, which are great propellants, but there are huge regulatory issues with it. They are deadly. So by using our combination, we're able to achieve a similar type of performance. And again, we don't depend on Russian engines. These are all made in the U.S. This is a whole new set of engines, U.S. made. I got 7,500 pound thrust engine, and it's a qualification run there in the photo at Dawn, the spaceport. That's that name, the GPRE, General Purpose Rocket Engine. Okay, 7,500 pounds of thrust, and it's nitric acid turpentine and ablative. Means it has a substance on the interior of the rocket that is something like a heat shield. Like when you see the Russians come in and in their capsule, and there's fire around the capsule. Well, there's an ablative coating on that vehicle that allows the heat to be dissipated as it outgasses and carries the heat away. So it's the same stuff that's on the inside of our engines. And I like to say we use an old Russian recipe for that. But it's a very high performing combination also. It's we get nearly the same type of performance as LOX kerosene without, again, all that cryogenic infrastructure. And it also burns really smoothly. So that's very important if you're trying to do precision type of placement into certain places in space for certain types of delicate instruments. We use composite, in fact that's an all-composite engine, except for its projection. And we have a kind of a plug-and-play replaceable chamber that we can put in if we decide to reuse that engine. And that engine's been used 3 times so far, and working very well. I think it has enough liner in it that can burn for a couple more hours, I'm sure. When we talk about rocket engines, generally a few minutes is considered really a long time. So this is roughly 5,000 degrees in the the chamber. So you're dealing with something that will melt the exterior of your, if you're using a metal exterior, an aluminum casing, or steel casing, it would burn right through normally. But this magical substance takes the heat out and dissipates it. And again, those are designed for mass production. You can see how large the rocket is. There's our intern, Sylvan, at the top, closing off one of the payload bays. And this first test flight of the CPM was in March, and he was closing those bays. There were actually four satellites on board. These were satellites that were test units for their future orbital flights with us. So these are the same people who bought our kits or were making their own satellites, set up test units to be flown under the G-forces and the vibration levels that this rocket provided. So it was really quite successful. And again, you can see the little supersonic gases. It's like a string of pearls down the center of that flame, called mock diamonds. That's these things are working well. It's kind of textbook. And again, that's launched out near Kundry Lake. That also is like a more than a half-ton worth of rocket there. Just leaves off the pad. I'll show you some video of it a little later. Rocket TV. We slapped a GoPro on it, and they gave us a nice. We're down there like ants somewhere, and we actually used that to capture one of the things that we tested during this launch. We don't just go out there and do this without permission. You have to have FAA permission and AST permission, which is the Office of Commercial Space Transportation Division of the FAA. This kit comes with, that's the cubic form factor at the top. There's a CubeSat kit, one of ours in the interior, but down below. But the CubeSat you see on the right, and it has pretty much the same capacity for the experiment, but the CubeSats traditionally weigh 1 kilo, and our CubeSat is 0.75 kilos. So it comes with all the parts you need to make an actual functioning satellite. There's some things you have to do. You don't just snap it together. You have to do programming. You have to do soldering. It has solar cells and power management software and all sorts of things. You have to actually send out the Gerber files to have your PCBs made, because it was made as an academic exercise. And we were selling these for $8,000. That was the kit and the launch. So nobody in the world could touch that. And that's why we have the 96 passengers already ready to go. These are the launch manifests that we have. These are CubeSats. It's a mixed manifest, we call it. CubeSats and CubeSats. There's a local one. You see Irvine on there. A Vietnamese program. These guys are great. In order to launch with us, they have to present a report that they've tested their satellite for vibration and heat and shock, things of that nature. So they said, well, that's too expensive. We can't do that. How are we going to do that? So they. About a month later, they sent us a bunch of pictures, and they said, we're going to test it for G-forces. And they had it. They had a big sledgehammer. Okay, across the floor, the G-force impact. They put it on a paint shaker to do a vibration testing, and they heated it up in an oven to test it for thermal. But really, people are thinking out there, and it encourages you to find novel solutions to maybe something you can't afford, because to have somebody test those things in a lab, if you could even find one, it'll be tens of thousands of dollars. So I like their methodology, and we have a forum for the builders, and we pass those bits of information out to everybody who's building. We have a number of satellites from Singapore, many Google and X Prize groups. I think there are 5 who are flying their hardware with us to test. We even have NASA payloads, so that's kind of interesting. I think there are 5 right now, and they're from the NASA IB facility. It's called. They test, verify software and different equipment. We have Saudi Arabian satellites. We have the Golden iPod, which is kind of a Voyager revisited. You remember the Voyager program? You're aware of that in the history of space. They sent out a big golden disc, record, all the sounds of Earth and music. Well, these guys are, they're going to send up an iPod, they decided. And that's going to be the new thing. So that's their, it's called the Golden iPod, just like the Golden record. Just like Pakistan, the Pakistani satellite, I was surprised that these were, up until this past month, heavily controlled by the State Department. This little satellite is considered a munition. And I had to have an export license to allow them to be shipped to places outside the U.S., anywhere. There are still restrictions on them, but they're not as horrible as they were before. We're hoping they'll eventually completely go away for at least the academic satellites. So that is, that's just one of the things you learn is how to implement the government. And actually they were fairly pleasant about it. It just became annoying and delayed sales. Boreal space, in terms of sky with theirs. And the Ruff's the space lion. Okay, that's a STEM program in Sweden. It is headed by an animated lion and a stuffed lion. So it apparently has a vast appeal. And the CubeSats on board from radically different backgrounds. Here you have Kentucky space, you've got Penn State, all in the hinterland of Kentucky out there. A Puerto Rican group, which is a middle school. This is actually that's the Inter-American University. There's another Puerto Rican group there too. You have the University of Puerto Rico and the Marcelino Camino Middle School. They're doing a STEM meteoroid impact study. And the children in that started around 11. And they're led by their wonderful mentors there. And again, they're not just snapping these together. They're learning how to solder, how to place the solar cells, design and have the PCBs fabricated and make modifications, how to program the Arduinos, which are now the basic microcontroller that we use. And we have arts projects as well. Project Calliope is a space music project that's run by Sandy and Nunez from Capital College in Maryland. And he wants to sonify the ionosphere and then distribute those sounds, if he gets any, as he said, to musicians around the world through a website. So for free use, they can have this satellite sounds. And we call it STEAM, because we have the arts in here. And we have music projects, we have a wide variety of items. Naval Postgraduate School, and West Point, 2 military academies. Naval Postgraduate School just succeeded in completing their first. They got 3. And they're somewhat more advanced than the other systems that are out there. They've encrypted delivery of information. We have United Kingdom, an Austrian group that is, again, an Earth art project. And this, probably the most exciting group there, the Brazilian Space Institute, and these 5th and 7th graders. There are 108 of them that started the program, including the 2 of Berlin, Brazil. They had a kind of a competition. It's kind of a Lord of the Flies thing. It's like they put them in a, I think they were like something like 20 groups or something. They built mock-ups of the CubeSat, and who built the best mock-up out of fiberglass and sand-off and cardboard and things like that. That group got to build an actual spacecraft. And they brought them up to the lab to visit, 12 of them. So they're serious about science. And when the satellite arrived there, it was like satellite games, was it? And it was like, it became like a national problem. So, you know, do we see that in this country? But at any rate, I thought that was pretty fabulous in terms of STEM outreach. And again, in that setup, it was half boys and half girls. So, you know, it wasn't exclusively a boys' club, which was nice. And they did some fabulous work on it. So they're waiting to launch. They have one going out on a Japanese launcher, and they have one going out with us. So the cool thing also is they, once they make the kits, they can kind of make as many as they want afterwards. We don't care because they're going to be launching with us very likely. So it's kind of a, you know, self-perpetuating sort of thing. Mexican satellite project Ulysses again is that's a space opera based on it's 11 different composers, and it has some kind of a relationship to soccer with 11 players. And it's all avant-garde music. Very, very successful program for them. The project for services working with Singapore. There's also many advertising agencies involved, like Espensa from Spain. The NASA also has CubeSats as well as the CubeSats. Galaxy Global bought one and donated it to the NASA educational program. This Institute of Advanced Media Arts and Sciences in Japan has 7. So that whole school has competing programs. You know, my satellite's better than your satellite. You know, so it works out really interestingly. More advertising with AKQA. Universities all over South America, Chile, Sao Paulo, and this David Lawrence K through 8 school, which is that's another really interesting setup. They're working with the Florida International University and a high school, and they have actually built a wonderful CubeSat. They have numerous videos online about how they communicate with the satellite, how to transfer a photograph in a very efficient way, and a number of things. But I have some photos of them. They were just featured in the Miami Herald. And the person running that program said these people now walk with a new swagger. They're in a traditionally underserved area and a pretty impoverished area in North Miami. So they're part of the satellite team. They love that. So it lifts you out of the everyday. You know, you're thinking about, you know, space is about ascension, right? You're taking something up, so it forces you to look up. More Japanese. Oh, there's also the 4-H and a Ute Indian youth retention project with Colorado State University. They're doing a satellite as well that seems to be catching on really nicely. We have the Doctor Who TARDIS in orbit. Okay. Yeah, I was really happy when that came in. That was fabulous. And they say that their CubeSat is bigger on the inside. Emmanuel Lesser is they have something called Space Booth, which are selfies from space. Okay. So that's kind of interesting. Portuguese universities doing straight science with that. Free to the National University of Singapore. Manhattan Satellite Lab, New York City Sat 1. A Slovakian satellite called Popular SK. Penn State University with their reloadable spare campus. They're doing one. And there's the Universidad Autónoma they have that in there twice, sorry. De Zacatecas, Mexico. That is 2 satellites there. And a South African satellite from the group called Makena. So these are people who, you know, not the traditional satellite makers, right? People from just, you know, remote parts of Brazil and you know, like people who are 11. I mean, it's just, you know, it's just very, very unusual. These are the actual people in some of the projects. And that whole group of Ubatuba, those are the guys that came up to visit. They actually, think of somebody taking, you know, your little brothers and sisters to maybe Brazil, you know, because we've succeeded in a project. Pretty cool. But at any rate, that's the Miami group there up at the upper left with that person on the left, and I've forgotten his name, but he won like the best educator of the year. And unfortunately, he went to meet with Obama like 2 days before he had the satellite in hand. It would have been nice if he could have taken the TubeSat to the White House. That would have been great. But maybe next year. At any rate, it's a vast you know, collection of different, you know, just different demographic, a different set of people making satellites than what we would see in the past. So I think it's a whole new age that way. You know, it is the age of the handheld satellite. And hopefully, you know, one will come to your campus soon to be built by you. Right? So I'd like to thank you guys. And if there are any questions, three others. Close out. Remember, this weighs, you know, like half a ton. See how it jumps up. It's terrifying, by the way. It felt like an earthquake, but it was thrilling at the same time. It's absolutely wonderful. You don't have to bear head. It's on the browser. It's not, it's under Cypress. So the small team, like I said, there's like 10 of us who designed it, built it, and are launching it. And again, this is a basic building block for all the vehicles that come. John, thank you. There's the payloads. Look at it.
Ignition sequence starting. 7, 6, 5, 4, 3, 2, 1.
Well, for example, when you started your company, before that you were in the garage, but did you just drop all of the previous career and just start this from scratch? Or?
No, those other careers came in handy in supporting the project. And sometimes it was doing all those careers at once in order to keep the project going.
But I mean, like a full-time, you weren't working full-time or anything, like you just...
No, I guess the closest I came to working full-time was, I think I was teaching something like 5 courses. And
okay.
that was
full-time.
That was pretty cool. Which I probably shouldn't have been doing. But yeah, but those were all in, they were like news. I think we were doing live news and some other things at Mount San Antonio College at the time. And that was easy for me to manage. I could do it. If I were doing something that was really perhaps work intensive, couldn't have been done. But my husband also, the co-founder of the company, was also teaching at Cal State LA, teaching chemistry, and at UCLA. So these are the things you have. Don't think that you have to have somebody give you a bunch of money and then you start. And you have to like bootstrap it, as they say. You have to, and sometimes you have to kind of go into hibernation for a while. You know, and sometimes we do things that people consider kind of silly, like launching beer bottles and things like that. You know, but sometimes we do cool things too, like we did a sound kind of manufactured the sound using different types of rocket engines for 2 films for War of the Worlds and Serenity. And we had an Academy Award winning team from Hollywood, a sound design team, that came out and did mic'd it for a whole day, took them to mic the whole thing out. And we did the firings for them. And we got to go to the theater and listen for our sounds. So there were multiple layers, but you could hear that Z4 is generally used. It was great. It was fun. So, we never discount any revenue streams. We're in reality shows. We're in all kinds of crazy things just to keep it going.
When you guys started your company and up to the point you are now, what are some of the most challenging things you ran into to get where you are right now?
What are some of the
most challenging things you ran into?
Most of the challenges were just being able to raise money, and we actually had a what's called a sounding rocket, which is now like really fashionable to do suborbital research. Everybody loves it. But in 1999. When we had the rocket and we were doing the launches, we couldn't give a launch away. It was strictly government. And nobody would touch it. Everybody's afraid to touch the commercial industry. Nobody would even go near it. We actually even got one of the first, it might even be the first commercial launch license in the US. That was in 2000 when we were going to be competing in what's called the QGITS prize, QGITS to space. But that was, we learned how to work with the Office of Commercial Space Transportation, and they learned how to work with us. Okay, they didn't know how to handle us. But we actually worked collaboratively, and that was an interesting experience. And we made some fast friends there, and they're considered a friendly. Yeah. So it was a good experience. But the paperwork was challenging. Insurance. And try to get, we go on launching a rocket this weekend. How much?
Must be astronomical.
You try not, or when you buy equipment, you try not to say the word aerospace because the price goes up. So those are just, you just have to learn how to deal with vendors and agencies and all of the above.
How long does it take to get one of those rockets back to launch?
Well, we started work on the current one about 2 months ago. But I don't know if you noticed on this one, it had some flat sides. We were looking at one way of joining the modules. We decided to go with a different method, and now we smoothed them out. So we did some radical surgery on the rocket. And it does not take a huge amount of time, somewhere between 2 and 4 months. And if we build one from scratch, and all the components are made and we're just plugging them in, that could take a month.
Composite, that's the same material that's been used by the Boeing most modern planes currently?
Yeah, the carbon fiber and resin.
And where do you guys get all of that material?
We just buy it commercially. And everything we buy that we don't make. It's just commercial off the shelf. One of the rules of the philosophy that we follow, which is the philosophy of minimum cost design, it's called, which is get things from industrial sources. You don't want to pay them, right? You have to get something that you can just buy every day and be sure that supply is going to be there. Standard industrial materials. So that's how we work. When we started, we made the mistake of having some things fabricated for us, at great expense and wiped out the budget. And we decided, well, we can't do this and make progress. So again, you have to be clever. You have to think outside the box, as they say, and it's challenging. It's challenging, and if you give up, well, then you fail, right? So you can't never give up. Give up, never surrender. Galaxy class, a very inspirational movie. But you must move forward, or you're dead. Right? That's sharks, I guess. Yes.
Are you hiring? And if you are, if I'm a Cypress College student, what sort of degree, what kind of background do I need to get to go and work for you? And when am I
That's a very good question, isn't it? For our here today. What we like to see is that people have been building things throughout their lives. Maybe they were amateur radio people. Maybe they tinkered around and tore things apart and put them back together. Maybe you made, home-built electronics. Did machining, did carpentry, know what it takes to actually build something. Okay? This is usually the missing component in, say, most curriculum. What's happening now is the new degree programs in mechatronics are trying, I believe, to bring those things together. We believe it's vital because you could be an engineer who's never built anything and you design something that looks perfectly great on a computer, but you give it to a machinist and it's impossible to make. And this happens all the time. This is what would happen. My husband worked at Grumman Aerospace in New York, but it was just Grumman, and General Dynamics. So these things would happen all the time. People would spend months and months and months on a project designing something that could not be built. So, you have to have a sense of how things go together, whether, just the way we designed the rocket to fit in a 40-foot cargo container. We may have built a gigantic rocket that we couldn't move on highways. People would make that mistake in the past too. And so, it's something you have to think ahead of everything that can go wrong, and everything down the line that could impact your cost and the cost to your customers, and try to mitigate all that risk.